Nevada Test Site, 1957. Operation Plumbbob, the sixth in a series of continental tests conducted by the Atomic Energy Commission to further our weapons development program. In terms of numbers of test devices detonated, this was the largest series ever attempted in Nevada. Some 30 shots were fired during the period early April through early October. While the main objective of the series was to test laboratory design of weapons, the Atomic Energy Commission and other agencies of the government once again participated in the detonations to amplify their understanding of effects. The Armed Forces Special Weapons Project participated in most of the 30 detonations with special concentration on 3 shots. The Civil Effects Test Group conducted its most ambitious test program to date to provide more detailed civil effects information to the public. Participating aircraft of all types homed into Indian Springs Air Force Base to perform their test missions. And the Desert Rock encampment was again reactivated in full force, giving thousands of military personnel of all services, including foreign troops, an opportunity to observe and perform certain assigned military duties in the proximity of a nuclear burst. Other observers on Plumbbob were the nation's newsmen, permitted by the AEC to view and photograph unclassified activities related to 9 detonations. Also at Plumbbob were representatives of a majority of the free world, observers from the NATO countries, the Near East, Far Pacific, and South America, invited by the United States government to observe the power unleashed by atomic force and our methods for coping with it. In executing the primary mission of test-firing new devices, a number of operational advancements were made on Plumbbob in new techniques for firing the test devices to minimize the fallout hazard. For it is well understood that if the fireball touches the ground or is sufficiently close to suck up earth dust or debris into the fireball, radioactive fission products will adhere to these materials and fall more rapidly as increased local fallout. Vaporized metal from tower bursts adds measurably to this local contamination. The airdrop technique, coupled with the airburst weapon used on previous operations, minimizes this problem, but radically reduces the amount of diagnostic data which may be obtained from the tests. Therefore, on Plumbbob, 3 basic methods were tried. Number 1, higher towers for given yields. Number 2, balloon-suspended devices. And 3, underground detonation. In Plumbbob, for diagnostic tests requiring massive shields or extremely precise positioning, 9 tower shots were fired, 1 at 300 feet elevation, 7 at 500 feet, and 1 for a device of higher yield at 700 feet, the latter 200 feet higher than any previously used. Balloon suspension, the second technique of positioning test devices at higher altitudes, eliminates steel tower contamination. This technique made its debut on Plumbbob with 13 devices detonated at elevations ranging from 500 to 1,500 feet. Most tricky step in balloon operation, the transfer of the weapon cab to the balloon, was accomplished only when surface winds did not exceed 15 knots, a condition which was predicted on the basis of wind persistence. These surface winds, known as balloon weather, accounted for only 7 days' delay. For comparison, unfavorable fallout predictions resulted in 55 days' delay on tower shots, 9 days on balloon shots. Once the weapon cab was connected in series with the main balloon cable, the 3 guy cables, connected to power winches at some distance from ground zero, were attached to the cab. After arming of the device in the cab, full control of the balloon was taken over at the control point. At his control panel, the operator visually monitored the raising and positioning of the balloon on 2 TV screens, the pictures being relayed by a microwave link. Both pictures display horizontal orientation. During the Plumbbob operation, balloon accuracy averaged 2 feet within the required position. A third approach toward easing the fallout problem and speeding up firing schedules was the investigation of underground test firing techniques. the Rainier shot. The aim here was to determine whether a device can be safely detonated underground with a nuclear explosion completely contained and still allow for accurate diagnostic instrumentation. In preparation for Rainier, an extensive investigation, including 2 large HE shots, was conducted to make certain that such a test would not endanger public health or damage property. Specialists of the U.S. Geological Survey studied the safety aspects and helped design the experiment. 5 independent and highly qualified seismologists, geologists, and geophysicists recommended by the National Academy of Sciences acted as consultants. The device was placed in a chamber at the end of a mine-type tunnel 1,900 feet long under approximately 800 feet of overburden. Vertically drilled holes, some as deep as 530 feet, housed shock instrumentation to measure acceleration, strain, and transient temperature rise. Rainier went off as planned, a 1.8 kiloton detonation. The tunnel was designed to be self-sealing so that the explosion would not vent to the outside air. After the test, the tunnel was core drilled from the mesa above to obtain radiochemical samples for determination of yield. The explosion and all of its radioactive products were contained within a radius of less than 200 feet from the shot chamber. The general method of testing weapons underground was proved to be safe, technically feasible, and economical for heavily instrumented shots. The Rainier results indicate that it should be possible to utilize the underground technique to safely test devices with yields of up to at least 50 kilotons. Parallel with improved testing techniques, other safety measures were strengthened. Chiefly, the off-site radiation monitoring system to protect the public against fallout was more elaborate than ever before. The Public Health Service, in charge of this field work for the AEC, had its monitoring equipment and checkpoints located not only in the immediate environs of the Nevada test site, but throughout the adjoining states. Inhabitants of selected nearby areas were film badged and briefed on radiation protection. Manned stations were supplemented by a number of remote data telephonic units, which transmitted the location's radiation level when its long-distance number was dialed. As test organization aircraft tracked and sampled each moving cloud, the Civil Aeronautics Authority kept all aircraft in the cloud's path at a safe distance. All in all, the care exercised by all agencies to minimize the fallout hazards set a high standard for Operation Plumbbob. Another radiation problem studied during Operation Plumbbob was the Project 57 safety test, in which the HE portion of a nuclear weapon containing plutonium was detonated on the test site. Purpose of the experiment was to investigate immediate and lingering plutonium contamination hazards should such an explosion occur accidentally, as in an aircraft mishap. After the shot, collection trays, air samplers, and animals, chiefly dogs and burros, were distributed over a 10-square-mile area in the vicinity of Ground Zero to get a time and distance index on the harmful effects produced, with some of the beasts kept in the area as long as 180 days. Post-mortem findings on the animals, collated with the test area's contamination pattern, are expected to provide answers to this grave problem. Inhaling a sufficient amount of plutonium can seriously irradiate the lungs, which ultimately may cause bone cancer. From the results of the Project 57 test, a yardstick will be provided for coping with this hazard. Although operational efficiency and radiation safety measures have an important bearing on continental testing, the primary reason for using the Nevada test site is to further the nation's weapons development program more rapidly and less expensively than can be done in the Pacific. 28 of Plumbob's 30 detonations were set off for the purpose of collecting information to advance the weapons development program. Of the remaining 2 shots, one was the underground technique test mentioned earlier, providing weapon designs of smaller size and weight with a greater delivery capability, achieving a greater economy in use of active materials, testing the utilization of available nuclear materials in various ratios in order to make the best use of the quantities available, assuring a high safety factor in weapons during handling, storage, and pre-delivery stages, securing basic information on higher yield design and techniques for devices prior to full-scale Pacific testing. The aims and objectives of the Plumbbob devices have been stated. Before this film is concluded, we will return to Dr. Johnson for a brief summation of outstanding conclusions regarding this comprehensive weapons program. All facets of weapon development at a test site hinge on digging out the data on internal device behavior during fleeting microseconds. Some of the fanciest thinking and most costly apparatus goes into these measurement and collection systems. Although the full diagnostic story is beyond the scope of this film, a glimpse of several instrumentation setups will give a fuller appreciation of the scores of programs involving diagnostics. As an example of cost reduction, to measure temperature as a function of time, a new line-of-sight method of recording using a series of reflecting mirrors was devised to replace the highly expensive kettle cable system. This measuring was done by an optical recording station housed in a concrete bunker in Area 2. The station also successfully took recordings from the tower, 4 miles away, through a relay of 2 additional turning mirrors. Alongside the central optical recording station was another innovation, a revolving 8-inch naval gun mount adapted to housing the primary detectors to pick up readings from each of the 4 tower shots. Here is a sample of a specialized diagnostic study, a hardware test. Stood the peace pipe, a 325-foot tall vacuum tube. The peace pipe tested the vulnerability of 150 functioning arming and firing components of future weapons systems. At 20-foot intervals in the vacuum tube, such items as X-units, contact crystals, and firing switches were tested for neutron, gamma, and electromagnetic effects. These effects were picked up by photographic and monitoring equipment installed under 13 feet of concrete at the base of the tower. Also, metal samples were hung on 2 pipes, respectively 10 and 30 feet from the shot cab, to test them for thermal and gamma erosion, as well as melting characteristics. On 8 other nearby towers between 200 and 300 feet high were perched functioning weapons complete with firing unit, but minus their nuclear and HE components. Here is another diagnostic experiment in which a picture of the radiation of burning gas in the center of a device was obtained for the first time, the pinhole neutron experiment called the PinX. Neutrons from the DT burn in the central gas region pass through pinholes about 25 feet below the device. A shielding of paraffin packed around the lower part of the device kept out any stray neutrons. Zirconium samples, mounted on a sled positioned in a concrete tunnel at the base of the tower, were activated by neutrons above the zirconium threshold. As soon as possible after the burst, a remote cable pickup was used to withdraw the sled from the highly radioactive tunnel. Readings obtained from the zirconium samples indicated the experiment's success, another step forward at one point along the wide diagnostic front in probing the inner workings of nuclear detonations. As in past operations, Plumbbob also served another function vital to the nation's security: the probing of blast, thermal, and radiation effects in the wake of a weapon detonation. The scores of tests undertaken on Plumbbob to secure effects information assume a greater importance than ever in this era of guided missiles and nuclear weapons delivered with increasing accuracy. The treatment of effects, a varied and complex field of its own, will be confined in this film to a broad brush sweep of a few major objectives sought in Plumbbob. Some effects have a strictly military application. How does an airburst react on steep and rolling terrain compared to flat land? How much protection does a gully behind a slight rise give a military vehicle? The Ruth's shot provided the first definitive answers to the military. Other effects pertain to the nation's civilian needs, such as the Federal Civil Defense Administration's improved family shelters and massive dual-purpose garage shelter. Often the effects needs of both military and civilian groups are interwoven, as in the study of what overpressure close in to the burst does to protective shelters. In Plumbbob, the effects on the instrumentation and test structures on Frenchman Flat, both above and below ground, provided important data for proper economical shelter design. Both military and civilians are also concerned with biomedical effects. Both need to know what is biologically acceptable to human beings in the atomic era. On Plumbbob, biomedical testing involved a welter of experimental field activity with blast and radiation tests on animals. One aspect of these tests leads towards finding out the interspecies relationship of mice, swine, monkeys, and burros as they relate to man. Aircraft structure effects. What is the structural response in the face of a nuclear burst on delivery jets like the F-89, the Navy A-4D, and the FJ-4? Plumbbob also included tests of the effects of nuclear bursts on the helicopter and the ZSG-3 airship. These tests were an initial step in a study of the feasibility of delivery of nuclear weapons by helicopter and airship. Midway in Operation Plumbbob, an historic Air Force event was set in motion on the Indian Springs ramp. 4 seconds more. All 3 planes broke sharply. The distance, 4,500 yards from the burst. Plumbbob marked the first time that aircraft had received nuclear blast input while banking away after delivery. 5 military observers stood directly beneath the burst, indicating the safety of interceptor nuclear rocketry to personnel on the ground below. This dramatic event produced important data on the effects of a known warhead at a stated distance upon aircraft and crew members. Neutron and gamma doses for the 3 crews did not exceed 5 REP and 3 Roentgens respectively. Whatever the effects project, military or civil, its findings assist the nation in building up our encyclopedia of nuclear effects data, including the creation of effective countermeasures. This was Operation Plumbbob 1957, where, in the sparsely populated desert area of southern Nevada, additional links in the nation's nuclear weapon chain were forged in atomic fire. In today's time of urgency, Plumbbob demonstrated again the value of Nevada testing, not only in proving out kiloton weaponry more expeditiously and cheaply than possible in the Pacific, but also in readying development for the next round of full-scale testing at the Eniwetok Proving Grounds. Plumbob's testing and effects programs achieved results which advanced United States weapons development a long stride forward, important not only to defend our shores and skies, but also to help maintain the strength of the entire free world.